Hi, my name is Manoj Anandan and this is my Advanced Functions CCT. Today we will be exploring logarithmic and exponential functions, specifically an investment problem found on page 507, question number 4. Question number 4 on page 507 states the following. Jerry invests $6,000 at 7.5% compounded annually. A. Determine the equation of the amount, A, after t years. B. Estimate the instantaneous rate of change in the value at 10 years, and C, suppose the interest rate was compounded semi-annually instead of annually. What would the instantaneous rate of change be at 10 years? After initially reading the 7.5% growth compounded annually, it is clearly apparent that this is an exponential function. After coming up with the equation for this exponential function, the question then asks us to calculate the instantaneous rate of change, which is a topic we covered in advanced functions in Unit 1. In order to determine the equation of the amount, we will use our prior knowledge obtained in grade 11 regarding exponential investment problems to isolate and analyze key variables in information. We will let I represent the growth rate, or in this case, the interest rate. This can be calculated by dividing the percent by 100 to get it into the decimal form, which in this case is 0.075. We will let PV represent present value of the investment, which in this case is $6,000 as stated in the question. We will let N represent the number of compounding periods, which again in this case is T years. And A obviously is the variable that we are trying to create an equation for. Now using the model provided here, we will sub in these values to determine a specific equation for this question. It is important to note that when subbing in I, it is added to 1, as this investment is growing in value. Any number under 1 would create a model for an investment that is decreasing in value, which is not a great investment at all. After subbing in these values, you are given a final equation of A equals 6,000 times 1.075 raised to the exponent t. Now that we've got done with the boring grade 11 concept and we have the equation for the exponential function, it's time to get into the grade 12 concept, which is instantaneous rate of change, or IROC. Question B asks to estimate the instantaneous rate of change in the value at 10 years. Before we can do this, we need to understand what the instantaneous rate of change, or IROC, is. Well, instantaneous rate of change is the rate of change or slope at one specific x-coordinate. It is also the slope of the tangent at that very same x-coordinate. IROC is often used to compare two exponential functions and analyze the behavior of a specific x-coordinate on both. This can be calculated both algebraically and graphically, and we will go through both. When estimating IROC algebraically, you are immediately faced with one significant issue. Up until grade 12, we have only been able to solve for rate of change when given 2 points. However, for IROC, we are trying to calculate the rate of change at one specific point. In order to bypass this, at least until calculus, we will find 2 points very close to the coordinate that we are attempting to estimate IROC at. To do this, we will subtract 0.001 and add 0.001 to that very same x-coordinate. After subtracting 0.001 and adding 0.001 to our x value, or in this case our n value, we are given 9.999 and 10.001 respectively. If you can recall from grade 9, in order to calculate slope, we need both the x and the y, or in this case the n and the a, of both of our points. In order to calculate a, we will now sub in our new n coordinates back into the equation previously determined. When subbing in n1, or in this case 9.999, we are given a y-coordinate or an a-coordinate of 12,365.29507. After subbing in 10.001, or n2, we are given an a-coordinate of 12,367.08374. It is important, although this is a dollar amount, not to round at this step, as we are dealing with very specific numbers, and any rounding could result in a drastically different answer. At this point, IROC becomes fairly simple, as the equation for IROC is the very same equation used to calculate the slope of any given line. M equals y2 minus y1 over x2 minus x1, or in this case, IROC equals a2 minus a1 over n2 minus n1. After substituting all the appropriate values, you are given a final answer of 894.335, which essentially means that at the x value of 10 years, this function is growing at $894.335 per year. And it's important to note that this is an estimation as based around the fact that we use 10.001 and 9.999 as our two approximate x values. Now, if algebra may not be one of your strengths, you might want to consider doing it graphically. When doing it graphically, it's important to note that the IROC at a value of x is equal to the slope of the tangent to the curve at that very same value of x. Now, you might be wondering what a tangent is. A tangent is a line that intersects with and is parallel to the curve at one specific point. So, in order to grasp an understanding of how we can use a tangent in order to calculate, or in this case, estimate the IROC, we have an example put up on the board. As you can see, the equation reads y equals 2 to the exponent x. So this curve right here models that very same equation. Now this line, if you notice carefully, is only intersecting that equation at one specific point, x equals 2. If you notice, any other point on that line is not touching the function, which is a key characteristic of a tangent line. So you might be wondering how we can use this in order to estimate IROC. Well, it's pretty simple. You find 2 points on this tangent line, so x1, y1, x2, y2, and you sub it into your very simple grade 9 slope formula. Now that we've completed question B, we can move on to question C. Question C asks us to recalculate or re-estimate IROC, taking into account that the interest rate is now compounded semi-annually rather than annually. It is important to note that when an interest rate is compounded annually, there's only one compounding period a year. So this 0.075 acts as the effective interest rate for 1 year, or the annual interest rate. Now that there's 2 compounding periods per year, we must divide this number by 2 in order to find the effective interest rate for each compounding period, which is now 0.0375. Now it's time to recall what n represents, which is the number of compounding periods. Now in question B, the number of compounding periods was simply 10, because there were 10 years and 1 compounding period per year, as it was compounded annually. Now that this investment is compounded semi-annually, there are 2 compounding periods per year. So you will multiply that 10 years by 2 in order to get a total compounding period number of 20. So as you can see, our revised equation reads a at 10 equals 6,000 times 1.0375 to the exponent 20. Now, in order to calculate IROC from here, we will use the very same method we used in question B. We will subtract 0.001 from our x value and add 0.001 from our x value, or in this case, our n value. So now we are left with 19.999 as our n1 and 20.001 as our n2. After subbing it into the equation mentioned right here, we will get a final answer for a1 of 12,528.45075, and we will get a final answer for a2 of 12,529.37322. After subbing in both points into our IROC formula, we are given a final answer of this. It is important to note that so long as we are estimating IROC using the method we discussed prior, the denominator will always remain 0.002 as we are adding 0.001 and subtracting 0.001 from a specific x coordinate. After looking at this final answer, you may be a little confused. An investment compounded more frequently should be a higher IROC in theory versus something compounded less frequently. But it is important to remember that this number is semi-annually. So in order to compare this answer to the initial answer, we must multiply this by 2. And then it is very clear to us that this IROC is significantly higher than the IROC we calculated when the investment was only compounded annually. I was able to verify this answer using Desmos by graphing both the function when it was compounded annually and graphing it when it was compounded semi-annually. The orange function represents the one compounded semi-annually and the red represents the one compounded annually. As you can see, it is very clear that the function compounded semi-annually grows at a much more rapid rate than that of the function compounded annually. Financial advisors and certified financial planners use both exponential functions and instantaneous rate of change in order to calculate and maximize investment return and manage clients' portfolios.